Now, where we want to go though really with the CDK is we want to move into the serverless world of cloud computing. And we want to create serverless oriented infrastructure. So that's where I'm going to go next. And I'm going to work my way through some of these slides. And so I've titled this serverless web APIs because serverless can apply to any type of server-side application, but we are going to be using it specifically for developing a web API. So that's the only reason I've tagged on web API to this. But the main thrust of this section is serverless for today anyway. Okay, and so again, see, some of you have come across serverless formally on this course in the previous semester. Some of you haven't, but just very quickly, what the implication of using a serverless approach towards I suppose the infrastructure that you want to use for your server-side application is that you as a developer, you are not concerned with provisioning your server instances, just as we were there in the demo. So we don't want to be lumbered with provisioning EC2 instances and configuring them and managing them and making sure they're always up and running. Now I know auto scaling groups can take care of some of that stuff for you, but a serverless relieves the developer, I'm saying here, of having to just provision servers at all. Servers are still being used, but it's just that we as developers don't need to concern ourselves with them. Also, as a developer, you don't need to worry about scalability of your server-side functionality. The serverless services that we will use will take care of scalability. By scalability, we simply mean that if there is a high volume of activity targeting your application, like requests coming into your server-side application, if there's a very high volume or a peak in the volume of requests hitting your application, then you'd like your application to scale up and deal with that volume. In other words, you would not like your application to suddenly become heavily latent in the responses that it's sending back to the requests that are targeting your application. You'd like the application to scale up accordingly and then scale back down once the peak starts to decrease. In the server-oriented world, this is something we had to be concerned with, and we had to configure it ourselves. Whereas in the serverless world, you let the platform take care of scalability. Number 3, upfront costs. Well, in the server-oriented world, as long as you've got an EC2 instance, which is a server, as long as that's up and running, you're paying for it, even though it may not be being used. You're still paying for it. Whereas in the serverless world, you only pay for however many requests are hitting your application. Availability is another thing. You always, in the server-oriented world, you have to make sure that your servers are always up and running. And if they crash, then you've got to make sure that they are rebooted and all of that stuff. Now, again, you can automate a lot of that, but you do have to automate the rebooting, etc. Whereas in the serverless world, again, that's kind of taken care of for you. I'm not getting into the detail of the how of these things because we don't have time for that stuff, unfortunately. Web APIs, I guess, hopefully everybody should know what a web API is, but I just said I'd cover it anyway. So web API is, I'm saying here there's some functionality running on the server, on the server side, whether it be on a serverless platform or on a server oriented platform. It's some functionality running on the server side. that functionality has got some sort of interface to the outside world. In other words, it can be connected to via HTTP, and your client can be anything. Okay. In our case, in this module, our client will be a web client, but all of the other are possible clients as well. And really, the functionality typically doesn't care about the nature of the client. All it's getting is HTTP requests. So that's a very kind of high level statement of what a web API is. Now, in the Amazon world, it has many serverless services, and I'm listing some of them on the left, and we'll only get to look at a small subset of them. So, for example, AWS Lambda is a compute service. In other words, it's an alternative to EC2. And we've got some other ones as well. I'm not going to go through them. On the right here, on the right really is, in a sense, by accident rather than by design, it's a snapshot of what we would like to achieve by the end of this module. And so let's just talk about the picture a little bit. What we'd like to have is our functionality of our web API implemented as Lambda functions, these things down here. So there will be many of those. Okay, there'll be a Lambda function for each part of our functionality, let's say. And these Lambda functions will be accessed externally. You know, if you go back to the previous slide where I had clients talking to my functionality, well, it's not going to be talking. My clients aren't going to be communicating with the Lambdas directly. They're going to be communicating with the Lambdas via what's called an API gateway. An API gateway is another one of the, it's mentioned there on the left, it's another one of AWS's serverless services, and it's specifically for developing web APIs on the server side. So requests are going to hit your API gateway first, and the API gateway will be configured so that it knows which of these Lambda functions it should send the request to, and the Lambda function does its thing. In many cases, the Lambda function will be interacting with a database. Our database is going to be implemented using the DynamoDB service. The DynamoDB service is one of AWS's serverless database services. There are others though. On the right here, we're using something called AWS Cognito. And AWS Cognito is AWS's serverless service for managing user authentication. So typically, you know, a login will target the Cognito service, and it will take care of authenticating the login request. And typically what it does is it returns some sort of a token, specifically a JWT token, and that token then is used by the client for making subsequent requests to your particular Lambdas, so that only people, only clients that are authenticated can actually trigger the execution of a Lambda. On the left, I have an S3 bucket. S3 is Amazon's object storage as opposed to a database. It's an object storage service, file service, you could typically regard it as. But we can use, or one can use the S3 service to host a website or a web app. Now, in the second half of this module, you will be developing a web app, which is your client app, and hopefully we'll get time to deploy that into an S3 bucket. And S3 is also serverless, although it predates serverless, but it is a serverless service. There are servers being used here, but we don't configure them. And so our entire infrastructure is serverless, and that's what we hope to achieve. But we've got a long way to go before we can get to there. So what I want to do is talk about some of the individual services that we need to use in order to achieve that infrastructure that I showed you on the previous slide. And the first one is AWS Lambda. And again, as I keep saying, some of you will have done some stuff on AWS Lambda in the previous semester. Some of you haven't. So for those of you that have, sorry about this slide. So what is AWS Lambda? It's an event-driven serverless compute platform. So computing means it's where you can have functionality deployed to, code, in other words. Serverless, we know what that kind of means now. Even though it's running code on the server side, we don't have to worry about the platform that code is running on. The AWS was going to take care of that. Event-driven means that it's some sort of event that will trigger the execution of our functionality, as opposed to, command line driven or user driven. It's some sort of event driven. And the AWS Lambda service is going to manage the what we deploy to the AWS Lambda service is an AWS Lambda function. And it's a function in the traditional sense of a function. We were developing TypeScript functions earlier in the module. So we can actually deploy something as small as a TypeScript function. We can deploy that in isolation to the AWS cloud. Like pre-serverless, what we deployed was an entire application, typically on top into an EC2 instance. But now we can deploy a small part of an application, one function, in isolation. And we use the AWS service to do that. So what we deploy is an AWS Lambda function. And that function has to be, when it does need to execute, in other words, when the event that occurs that triggers the execution of our function, then what actually happens behind the scenes is the AWS service, it creates an instance of what's called a micro VM instance. And it runs that micro VM on one of its many servers. And having created the micro VM instance, it loads the appropriate operating system into that instance that will be controllable by your infrastructure code. And then it loads the actual AWS Lambda function into that micro VM instance. And then it executes your function and passes it the event that triggered that whole process. And if there are no other events immediately following that event, then it simply throws away the micro VM instance. It trashes it until another event occurs that's targeting your function, and it goes through the same process again. Creates another micro VM instance, loads up the relevant operating system, and loads your function into it, passes the event to it, and executes the Lambda function. Now, it probably holds on to the micro VM instances for a while in case there are subsequent requests. Doesn't want to have to go through that long initialization process every single time if it can avoid it. So it does warehouse, if you like, these micro VM instances for a short period, or obviously can't hold on to them for too long a period. So that's kind of what happens behind the scenes. So what I'm saying here is that this whole Lambda service, what it's all about is, it's about custom code, which is the AWS Lambda function that you write, custom code that runs in an ephemeral container. The ephemeral container is this micro VM instance that I was talking about. Ephemeral essentially means that it kind of creates an instance of the container, the micro VM, and it just throws it away if it doesn't need it shortly after having created it. Another term for this whole area is FaaS, or function as a service. So then this again kind of describes what a typical serverless application at a very, very high level kind of looks like. So here is the Lambda function that we write. the execution of that function is managed by the AWS service, AWS Lambda service. And so the event that triggers the execution of your Lambda function, that event is first of all grabbed by the AWS Lambda service. And based on your infrastructure code, it knows, well, this event needs to be passed to this particular Lambda function. And it passes the event to the Lambda function, and the function does its thing. And, the function can do anything, include possibly talking to other AWS services. So this could be DynamoDB service or the SQS service or whatever. So the key kind of parts to this diagram is the event source. So the whatever caused the event to occur, that's what we refer to as the event source. And the event source can be anything really. It could be an external HTTP request, which it will be in the case of a lot of our web APIs. Could be a HTTP request, as I'm saying down here. Or it could be a change in a data store state. So the data store could be a DynamoDB database. So if you can imagine you had a DynamoDB database here, and there was a new record added to that database, the addition of that record caused DynamoDB to fire an event, as we say. And that event is what is triggering the execution of our Lambda. Or you might imagine an S3 bucket over here, or file storage service. And whenever a file is uploaded to the S3 bucket, that causes S3 to fire an event. And that event is what triggers the execution of our Lambda function. And the firing of the event and the link between the S3 and the execution of this Lambda function, you have to describe that in your infrastructure code. And hopefully we'll get to, we won't actually, as it turns out, but not in this module. In another module, I do that. But anyway, in our case, it'll be always HTTP requests. That will be the source of the event for triggering our Lambda function. The Lambda function can be written in any language, pretty much any language that you wanted, those that are supported by the AWS Lambda service, and that's a growing number of languages. We are going to be writing our Lambda functions in TypeScript, but you can write them in other languages. And in fact, within one application, within one stack, you could have a number of Lambda functions, and they are using different source code languages. So you could have a Python Lambda, TypeScript Lambda, a Go Lambda, all within one stack, because the Lambdas are completely independent of each other. So you pick the language that's most suited to the nature of the processing that's done by the Lambda in general, but we'll be using TypeScript in all cases. There's some general stuff here about the Lambda service. It takes care of auto scaling. If I just briefly go back to this one, let's suppose there's a high volume of these events concurrently happening. What the Lambda service does is it'll actually create multiple micro VMs, and each one is going to be running its own copy of the Lambda function. And the Lambda service will distribute the events between the various micro VMs, or between the various running instances of your Lambda function. So it scales up automatically, does that automatically for you. Now, there is an upper limit to how many parallel micro VMs, and you can control that to a degree. But that's how it deals with scalability. And it just gets rid of these micro VMs then as the volume of events start to decrease on the left. So it takes care of auto scaling, takes care of load balancing between those multiple micro VMs that are running in parallel. It takes care of the managing the operating system that's running within each micro VM. It makes sure, okay, you might have multiple micro VMs, concurrent micro VMs, all running the same Lambda, and they may actually even be running on the same hardware piece, hardware, but the Lambda service will ensure that each execution of your Lambda function is completely insulated from the other running executions as you would want it to be. And finally, and most importantly, I suppose, the Lambda service will take care of providing the necessary utilities that the function needs. And by utilities, we mean the CPU power that it needs, the RAM memory that it needs, and the network bandwidth that it needs. The Lambda service takes care of provisioning those at runtime for your Lambda function. On the right, I'm saying that the characteristics of this AWS Lambda functions approach is that, you know, a function now is the unit of what I'm saying is the unit of scalability, as I was kind of describing there a moment ago. Whereas previously, scalability happened at the application level. You had multiple copies of your application running on multiple EC2 instances. That's how you scaled up and scaled down. Whereas now you scale up at the function level. So it's far more fine-grained. Number two, your function is the unit of deployment, whereas previously the unit of deployment was your entire application. But now you can essentially deploy particular part of the application in isolation from other parts of the application. Thirdly, well, the stateless nature, clearly, if you've got your Lambda function running inside the micro VM, and you know, it's obvious, I suppose, but if it throws away the micro VM and another event occurs, the next execution of your Lambda function has no knowledge of the previous execution of the Lambda function. Obviously, I guess, you know, but so that's what we mean by stateless. Whereas that was not the case in the pre-serverless world. You could have some sort of history, and that might be beneficial. Okay, if you want to simulate that in the serverless world, you've got to approach it another way. There is there's a limit to how big your Lambda function can be in terms of how much processing it can do when it's executed. And I think the upper limit, although it might have increased, but initially anyway, the upper limit was it could not run for over the max was, I think, 15 minutes. So if it was really heavy processing that took more than 15 minutes to complete, then you could not use the Lambda service as a way of implementing that piece of functionality. What you would tend to do is implement that type of functionality, not so much as a separate application running on EC2, but you might run it as a Docker container running on, let's say, something like AWS Fargate, which is a serverless container service. Also, the pay per execution characteristic, you know, you only pay as the user of the AWS cloud, you only pay for how many times your Lambda function executes. Whereas in the server-oriented world, you were paying for your EC2 instances, whether it was running and handling any requests or not. So Lambda function, in terms of the code that you write, this is what it looks like. It's the anatomy, I'm saying, of a Lambda function. There's the actual function itself. You can call it anything, but conventionally we refer to the function, we name it handler. So handler is my Lambda function. You also have what's called initialization code, and in the initialization code, which is outside of your handler function, that is where you put typically things like database connections. So if you have to connect to a database, inside here you would be doing your reading and writing to the database, but to actually get the database connection, you do that outside of the handler. Or if you were communicating with other services like SQS, the connection you make to the other services, that code should be put. It doesn't have to be, but it's bad practice if you don't put it outside the handler. And I'll explain later on why that's the case. Or do I do kind of mention it here? The handler itself, clearly it's an asynchronous function because it's being invoked over the network. Everything is happening over a network in the cloud, of course. The handler function takes two parameters, but really the first one is the one that we use mainly. We don't tend to use the second one. And based on the name, the first parameter that will contain all of the information about the event that triggered the execution of your Lambda function. Typically would contain some important data that the function then uses as part of its processing. The context really more relates to if you want to drill down into the runtime environment and you want to get access to some part of the runtime environment. In other words, the micro VM itself, but that's rare, and we never need to do that. At the bottom here, I'm saying the initialization code executes before the handler. Okay, for cold starts. Like what actually happens when you're when the Lambda service creates this micro VM instance, what it does is it executes the initialization code and then it executes the handler. And let's supposing there is another occurrence of the event immediately after, and it decides that it's going to use the same micro VM to process the subsequent event. Well, the processing of the subsequent event, it does not need to run the initialization code this time because that has already been executed by the micro VM. You know, it's made the connections to the external services. So we don't need to do that again. And that is quite expensive from a time and latency point of view. But for the subsequent event, provided we're using the same micro VM instance, the initialization code is not executed, only the handler is executed. And so we get the benefit of not incurring the latency associated with the initialization code. When it does have to run the initialization code, we refer to that as a cold start of the micro VM. When it does not have to run the initialization code, we refer to that as a warm start of the micro VM. And I'm mentioning those two terms down at the bottom. So your Lambda is a compute service, and so it's going to consume CPU power. It's going to need some RAM memory. It's going to need some network bandwidth potentially. And it needs those three utilities, and we can configure those utilities in terms of how much of each of them do we need for our Lambda function, because it's going to vary from function to function depending on what processing the function does. Now, rather than allowing the developer to configure each of those three parts of the Lambda functions configuration, what the AWS team decided was they would just allow you to configure the amount of RAM that your Lambda function needed. And then based on that, the Lambda service itself would compute how much CPU power it should provision for your Lambda function and how much network bandwidth. So this was a conscious decision made by the AWS team. Rather than giving the developer too much control over the utilities that your Lambda function needed and potentially, configure them incorrectly, it just gives the developer one dial that the developer can control. So it's the RAM dial. So the more RAM that you allocate to your Lambda function as part of its configuration, that determines how much virtual CPU power will be provided for the running of your Lambda function at runtime, and also how much network bandwidth. And I'm explaining on this slide, well, not explaining, I suppose, but outlining on this slide how we configure the RAM. So it's the smallest amount of RAM that you can allocate is 128 megs, and it can be up to a max of 3 gigs which is pretty significant, as you might imagine. And I don't really want to get into this because we're not going to be concerning ourselves with this sort of fine-grained configuration of our Lambda functions. Obviously, it is important because the more RAM that you ask the AWS cloud to provision for your Lambda function, the costlier it is to run your Lambda function. Okay, quick demo. A very quick demo. Let's see. Close that off. So it's a CDK app again, and let's get straight to the important part, which is my stack file, which is here. And my infrastructure comprises of one thing, again, for simplicity's sake. And in this case, we are creating a Node.js function construct instance. So Node.js is another L2 construct. And it's part of the Lambda, part of the AWS library. And again, I need to link my Lambda function with a stack. So I'm linking it to the current stack. I just give some sort of name to my Lambda function. And the rest then is the configuration for my Lambda function. And for this particular case, although it's not important, I'm saying I want ARM24 architecture. I want to run on a particular type of hardware. I mean, it doesn't really need to. This one makes it a little bit more sense to us. I want my micro VM to have Node version 18 installed on it. Here I'm just specifying the actual where my Lambda function is implemented, which is here. Look at that in a second. And here I'm telling the Lambda service that if my Lambda function runs for more than 10 seconds, then it should essentially it should interrupt the micro VM and cause an exception and send back the exception response back to whoever triggered the execution of the Lambda function. Note, I'm not specifying any RAM memory here. I'm accepting the default. And the default is the minimum, which is 128 meg, and that's fine for what this particular Lambda function does. So there's very little configuration there. And that's about it, really. The only other thing I'm outputting, the only other thing I'm including in this stack is here. And sometimes you want to output some information back to the terminal when you do a CDK deploy. In this case, I want to output the full name that the Lambda service assigns to my Lambda function. The name will comprise of the stack name, the name that I specified here, plus a hash value. So it'll be some long kind of string. And I do want that to be output to the terminal because I'm going to be invoking the Lambda function using the CLI. But that's it, right? Now, my stack file, nothing interesting in there. Sorry, my app file, nothing interesting in there. Again, I'm just creating an empty CDK app, and I'm creating an instance of my stack, which I've just shown you, and I've attached it to my app. So that's it. If I do CDK deploy, And if I switch over to the Lambda service, so it's still deploying. Okay, now it's done. And I also have there's the name, the full name of my Lambda function. And this line was generated by this statement in my infrastructure code. And if I flip over to the management console and just go to functions, do refresh. There's my function. And the function name corresponds to what I saw on the terminal there. Now, the only way I can trigger this function is by using the CLI. So my CLI command is going to look like this. And if I just substitute in the name of the function, now I didn't look at the function, but let's quickly look at it. Pretty uninteresting. Here is the implementation of my Lambda function. And it does nothing other than it does a console log and it returns this response. Yeah, that's all it does. So if I run it, now when you run it using the CLI, the response that comes back from the Lambda service, you have to put that into a JSON file locally. And so I'm just saying, put the response into a file called response.json. And so I ran it earlier on, so I'm just going to delete that for now. You would overwrite it anyway, but okay, so we're good to go. Um, this is just coming back from the lab. This is just coming back from the AWS, sorry, from the Lambda server saying, look, everything was okay, but the actual response from the Lambda function is inside in my response.json file. And so if I open that up, and surprise, surprise, if you scan it across, that is consistent with the code that I showed you. So this kind of message, for example, that's consistent with what my code was actually saying it should return back. The console log, this is the last thing I'll cover with you. The console log, where does that go? Because we will be using console log quite a lot, mainly as a kind of debugging aid. It's pretty primitive, I know, but where do console logs go? Where can you see them, the output from them in the cloud? And the answer is there is a service called the Cloud Watch service. The Cloud Watch service is used by many other services, including Lambda. So if I go over to the Cloud Watch service, and if you select log groups, there will be a log group for each Lambda in your serverless application. There would also be log groups for the other services that use CloudWatch. Won't arise, I don't think, in our case, but it will mainly be the Lambda service that will be using CloudWatch. The log group names are constructed by CloudWatch itself, and the name is kind of indicates which service this log group belongs to. So you can see from the name of this log group that it's coming from the AWS Lambda service, and the rest of the log group name is specific to our Lambda function. So it's a kind of contains a bit of the stack name and the actual function name. So if I click on that log group, a log group is comprised of log streams. And in the case of a Lambda function, there'll be a log stream for every execution of your Lambda function, there or thereabouts. If there are two or three, if there are a number of quick consecutive executions of your Lambda function, then they'll all be packed into one log stream. But not in our case. We only had one execution, so there's one log stream down here at the bottom. And if I click on that, now I can look at the detail of the log stream. And in particular, if I pick out this part of the stream, where is it? Is it here? Let's see. Oh yeah, there it is there. So that there, I was invoked. That's consistent with what my console log statement wanted to output. And as I said, you'll be using console log as a debugging aid, really. As I said, it's quite primitive, but there are more sophisticated ways of debugging Lambda functions, but we just don't have time to look at the more sophisticated ways, as it turns out. So we'll just have to use console log instead. So that's our first example, very simple example of using the CDK to deploy a serverless app. And calling it an app is a gross exaggeration because it just consists of one Lambda. But you have enough information to go to the lab associated with this section, and you will be able to complete the first part of the lab, which is this part here, standalone Lambda functions. From there on in, then I need to cover some more stuff before we can do the rest of this lab. Now, in this lecture, I want to continue with our discussion on serverless web APIs. So the slides that I'm going to be working my way through are still in this deck here. And where we left off, you remember, we got to the stage where we used the CDK to provision a Lambda function. And then we invoked that Lambda function using the CLI. And I also showed you that if the Lambda has a console log statement or statements in it, then those log statements can be viewed using the CloudWatch service. So we'll pick it up from there. And in my slides, we're getting to here. Now, the title here is Lambda integration, but I'm not talking about integration here in terms of what your Lambda can do, because your Lambda function can communicate with any other AWS service. By Lambda integration here, I mean what services can trigger the execution of your Lambda. And this goes back to the kind of event sourcing idea. which the demonstration that I've just given you there doesn't have any illustration of event sourcing though. So it turns out that quite a number of the AWS services can potentially be the source of the events that trigger the execution of a Lambda function. And we'll see some of them in the next few weeks. Well, one in particular, I suppose, and we'll see others later on in this module. So I'm not going to go through the services that I mentioned here. Just suffice it to say that all of the services that I've mentioned here, some of them you're not familiar with, some of them you are. If you just take S3, for example, you can trigger the execution of a Lambda as a result of some state change in an S3 bucket. And I've kind of mentioned that already. But you've got to express that in your CDK code. And the CDK framework will take care of setting up the infrastructure to achieve that. So there's quite a number of services that can be the triggers for a Lambda function. The way it's modeled from a kind of an implementation point of view is you can have synchronous invocation of your Lambda function, an asynchronous invocation, or you can have what's called a polled-based invocation of your Lambda function. So there's three different models, and the various services that I'm mentioning up here, they are restricted to using one of the models, and this is all kind of prescribed by AWS. You can't do an alternative. So whichever service that you're using, you're using as the trigger for your Lambda function, you've got to look at that service's integration with Lambda and follow the particular programming model prescribed, whether that be synchronous, asynchronous, or poll-based. I'm going to talk about each of those briefly. We'll experience synchronous in the next week or two. And so for the synchronous, which is usually the more straightforward kind of model, really, for a synchronous invocation, the services that follow that model are, well, if you invoke it from the CLI, which I've just done, so we were essentially using we're invoking the Lambda function, and the CLI waited until the Lambda executed and responded back. That's typical synchronous invocation. Also, if you want to write an application that's using an SDK, so for example, you could write a Python script or indeed a TypeScript script, run that TypeScript locally on your machine, and use the SDK to communicate with a Lambda function. But the communication is synchronous as well, because the particular application that you have written is going to wait for the response. API gateway follows this synchronous model. We'll look at API gateway next week, I think. You can actually link up a load balancer with a Lambda function. Doesn't always, Lambda load balancer isn't always the front for an EC2. So we won't be looking at that, but that is possible. But if you do integrate a load balancer with a Lambda function, the communication between the two is synchronous. And there's also something called function URLs, which I'll illustrate in a minute to you. You can actually get the Lambda service to generate a URL for your Lambda function, and then you can invoke it from a browser or some other type of web client. But the communication is synchronous as well. And, you know, the picture here kind of demonstrates some of those. So if we're using the AWS CLI or the CDK, and we saw that there a moment ago, you invoke it, the Lambda executes and it responds back. If we're using API gateway, which we will be doing next week, API gateway is this serverless service for developing web APIs. But either way, your client, presumably your browser, sends a HTTP request to this API gateway service. It communicates with the Lambda, and you have to, in the CDK code, you have to kind of set up this integration here. The Lambda executes, the response comes back, and the response is sent back to the client. But again, it's all synchronous. In the function URLs idea, you can actually invoke directly from a web client. You don't have to go through the API gateway. You can have a web client that communicates directly with a Lambda if that Lambda function has a URL generated for it. So that's synchronous invocation. And let's see an example of that happening. And in this example, I'm going to use the same CDK application that I had there a moment ago, my single little Lambda, but I'm going to get the CDK to generate a URL for that Lambda, and that will allow me to invoke it from a browser or from Postman. In addition, you can actually configure the URL to be a private URL. And in that case, there has to be some form of authentication with the HTTP request to the Lambda function. So how do I get the CDK to generate a URL from my Lambda function? So I'm just going to, because I've prepared this earlier on, I'm going to check out, did I make any changes there? No, I'm going to check out this branch. Again, let's look at the CDK code. The Lambda itself hasn't changed. I don't think it's much the same as before. The CDK code. Okay, I create my Lambda instance as before, and this is how I just get it to generate a URL for me for the Lambda. And so I'm adding a function URL. That's okay. You can configure the URL to be public or private. Let's start off by making it public. So the authentication type would be none in this case. And you can also configure a CORS setting for our CORS configuration for your URL if you want to, but I'm not going to in this case. And I'm also getting my CDK stack to output the generated URL for me so that I can then just use it. So that's my stack. Let's redeploy. Okay, and let's see, here's the URL. So if I just click on it, then voila, I get my response. This is the response that was actually generated by my Lambda function. And let's confirm that that is still what the Lambda function generates. Yeah, it's the same. That's the, see, there's a text message that it generates, and that's what I get back in my browser. That looks good. If I now, let's say I want to make that URL. So I am triggering, what am I doing there? I'm triggering the Lambda via a URL that has been generated for it by the Lambda service. That ability to associate a URL with a Lambda, that's a fairly recent feature that was added to the AWS Lambda service. It's only been around since 2022, I think. Now, you can actually make that URL protected or private. And the only form of authentication that's supported for private Lambda URLs is based on the IAM's authentication. In other words, SIG-v4, if you're familiar with SIG-v4 from last year. So to make my URL private, I need to just change the configuration slightly of the stack. As in here. You can see there are only two options available to me, either public or private based on the AWS IAM authentication model. Let's save that, redeploy. So it's all pretty straightforward so far, really. I think there's nothing too much too interesting happening. When we start getting into bringing a database into the equation and API gateway, then we'll have a richer, we'll have a set of Lambdas all sort of sitting behind an API gateway, and that will provide obviously more functionality. And we'll just get the Lambdas, most of them just interacting with a DynamoDB database. So again, it's fairly standard kind of stuff, admittedly. The theme, though, is it's all based on this kind of serverless model. So here's my URL in this case. But clicking on it now isn't going to work because it's a protected URL, but let's try it anyway. Okay, so I get a forbidden. So now I'm going to switch over and use Postman as a way of invoking this URL. And so I'm going to set up a GET request, HTTP GET request to this particular URL, but I need to provide my AWS access key credentials, and Postman takes care of using those credentials to generate the relevant authentication headers and indeed some query string arguments, generating all of those and sending them with the GET request to the URL to the AWS Lambda service. The Lambda service checks the authentication credentials that have been passed to it, and then it will either allow it to execute the Lambda or not. So if I bring up Postman, now we will use Postman quite a lot in the first half of this module because it's going to allow us to test our serverless web API when we eventually get to develop those. But for this particular use case, what we do is create a new HTTP request. Kind of assuming you may have used Postman already, but some of you may not. So create a new HTTP request, which I've done. Give it a name, and then essentially fill out this part on the right. So if I grab the URL that was generated by the CDK for me, Then select the Auth tab. And we need to select the authentication type, which in this case is AWS SIG-v4, which you'll find down here. And when you select that, then there are some fields that you need to fill out on the right-hand side. Now, the access key and the sort secret key, they are the keys that were generated for you when you created your IAM user. So you'll get those off your own local machine. And so I've pasted in my 2 keys into these entry points. And also, if you expand the advanced configuration, you also need to fill out the region, which in our case is EUS1, and just set the service to Lambda. The rest you can leave blank. And so what Postman will do is take those details and use them to create the relevant authentication headers and also a query string parameter. And now if I just click send, then the response that I'm getting back here, that is consistent with the response that my Lambda would have created, which is that. So that seemed to work okay. Just to prove it, that it doesn't work when it shouldn't, I guess, if we just kind of mess up the keys. So if I just make a small change to my key, either the access key or the secret key, save it, and then try and do a send. And I'm getting back an error message, which would be generated by the Lambda service itself, because it's the Lambda service that will perform the authentication check. That's the synchronous model. The asynchronous model I'm just going to talk about, but we won't demonstrate it because it's a bit more complex in terms of setting it up. The asynchronous model is relevant if you have, if you want to associate an S3 event as being the event source for triggering your Lambda, or if you're using a simple notification service, if you want that to trigger a Lambda and some other options as well. Like if we demonstrate the S3 one might be the easiest one to explain. The idea is somehow, some way you have access to an S3 bucket, and let's say we add an object to that bucket. We have our Lambda function over here, and we've configured the Lambda via our CDK in our case, such that we want this Lambda to be invoked whenever a new object is added to the bucket. When that eventually gets deployed, what the AWS service does is it generates a queue, and when the event occurs within the S3 bucket, the S3 service will communicate that event to the AWS service. The AWS service will know that event is associated with this Lambda, and it will add the event itself to this queue. And there may be many of them, so the events themselves are queued up in this structure here, which is all created behind the scenes for you by the AWS service as a result of our CDK code. And it invokes the Lambda then. It triggers, the AWS service triggers the Lambda to go and retrieve whatever events are in this queue. So what it actually will receive is a batch, or it could be a batch of just one, but it receives a batch of events that are linked to the S3 bucket, and it just processes them. But how is this model asynchronous? It's asynchronous because this is my client away over here. and my client is not waiting for the Lambda function to process the events. All the client is doing is putting an object into the bucket, and then it's finished as far as it's concerned. The triggering of the Lambda happens asynchronously behind the scenes between the S3 service and the AWS Lambda service via this kind of queuing mechanism that's managed for you by AWS itself. So the Lambda service up here, I'm saying the Lambda service places the events in a queue. The Lambda service, if for whatever reason, so it will trigger your Lambda, and the Lambda will process a batch of events from the queue. If for whatever reason the Lambda crashes, we needn't get into the details of why, then if the Lambda function crashes, then the Lambda service will actually retry the invocation, or it will re-invoke the Lambda again to try and complete the processing, and it does that 3 times. I think it's pre-configured to retry it 3 times. Eventually, it gives up on it, and we kind of have to deal with the consequences programmatically some way. But the Lambda service will take care of re-invoking your Lambda on a number of occasions to complete the processing. And because of that, you've got to make sure that I'm saying here that your Lambda implementation is idempotent, because what might happen is the Lambda gets invoked with a batch of 10 events. It processes the first 5 and then crashes, which means the Lambda service will re-invoke your Lambda function, gives it the batch of 10 again. Now you've got to make sure, because it's already processed the first 5, whatever the nature of that processing is, it needs to be idempotent, because it is actually going to process the first 5 all over again. So you've got to be aware of that, is all I'm saying. I'm saying here it does 3 retries using what's called a an exponential backoff algorithm. All I mean by that is that the second execution, it will delay the second invocation for a period, let's say 3 seconds. If the Lambda still crashes, then the Lambda service will delay for double that, 6 seconds, and then tries again. If it still crashes on the second occasion, it will wait for double the delay time, which we're now up to 12 seconds, and then invoke it again. And now we've had 3 retries. At that stage, it gives up. And we can talk some other time about how we clean up all of this stuff. But the Lambda service takes care of retrying your Lambda function on a number of occasions in case of failure. Why would we take this approach at all? Like, you might ask, why not have a Lambda here so that the client sends the object to your Lambda function processes it, and then puts it into the bucket? That would be a synchronous approach, because now our client, because it's invoking the Lambda directly, our client is waiting for the Lambda to do the processing and put it into the bucket. Whereas in the asynchronous model, all it's doing is just put the object into the bucket and it's finished. And the reason you might take this asynchronous approach is because, well, maybe the client doesn't really need to doesn't care about whether the processing has been completed or not. All it cares about is, has the object been added to the bucket? The client doesn't have to wait for all the processing to happen. And that means our client-side application there's a faster response to the end user as a result. Okay, all of the processing hasn't been completed, so the end user can say, just because they got a response back, that all of the processing has been completed. But there are occasions when this asynchronous model is is suitable. So we've got the synchronous model, we've got the asynchronous model, and the third option is this event source mapping model, which is kind of odd, kind of an odd one out, but it's there for technical reasons. We don't need to, nor have I studied in detail the technical reasons for it. But the way this third model is implemented, and it applies if you're using what are called DynamoDB streams. So the idea here is your client is, let's say, updating this DynamoDB database, which it's just an ordinary database as far as we're concerned. It's adding records, it's modifying records. And we want a particular Lambda function to carry out some processing as a result of some change to the database. Again, we don't have to go into detail of what the nature of the processing is, but we want to trigger a piece of functionality every time there is a change in my database state, as in new record added, record has been deleted, record has been updated. So that's the event that I want to trigger my Lambda function, the change within my Dynamo database. And so the way it works, again, from a CDK point of view, you provision the Lambda function, you provision the DynamoDB database, and you express the fact that you want this Lambda to be triggered by the state change in the database. And then the AWS service sets up this kind of infrastructure. And the way it works in this case is it works on a polling basis. The AWS service periodically asks the database, have you experienced a state change since I polled you the previous time? And there may be a number of state changes between two consecutive pollings. So the AWS service does that polling for you. If there have been a number of state changes, by the way, every time there is a state change in my DynamoDB database, that state change is logged internally by DynamoDB. And we refer to that log as a stream. And so when the AWS service polls the DynamoDB database, it essentially gives that stream of logs as the response. That stream is put into this intermediate queue. And yet again, the Lambda service is provided with the contents of that queue as a batch of events, and it processes them again. But the key point here is that the AWS service is polling my event source for events, whereas in the asynchronous model, if I just quickly go back to it, in this model, the event source is telling the AWS service about the events. It's providing the events to it. And okay, the AWS service puts them into the queue. So there's a different kind of invocation sequence going on between this asynchronous model and the event sourcing model. This event sourcing idea is also used by SQS, which is a service that we'll use later on. It's also used by Kinesis streams, which we won't use. So we will see later on an example of where we can set up a Lambda that's triggered by a DynamoDB database state change. Now, the Lambda service, in fact, pretty much all of the services, they provide an API interface so that other services can communicate with them. And this is the case with Lambda. So that's what I'm trying to represent in my picture here. I've got my Lambda service. And it has an API interface. And that's what we use. So for example, when we were using the CDK to talk to our Lambda function, our CDK communicated via the API to the actual Lambda. So in effect, it's asking the API service to send an event to a particular Lambda. And the same applies for any other service that will want to talk to a Lambda. So our S3 bucket case, it's using the API provided by the Lambda service as well. Now, this API, essentially it's just a HTTP interface, although strictly speaking, it's a HTTPS interface. So these are all kind of network calls that are being made here. Now, in terms of on the client side, you don't want to be making raw network calls. And so for that reason, the API that the service provides, there is an SDK provided by the AWS service that just makes the invocation programmatic rather than having to make HTTP calls. So that's what I'm trying to get across here, that each of these services that are trying to invoke a particular Lambda function, they're using the AWS SDK package to facilitate the communication. And so if we wanted to write our own piece of code to communicate with a Lambda function, we would use the AWS SDK as well. And that's irrespective of whether it's the synchronous or the asynchronous programming model. I'm saying here you can pass any type of event, any type of payload can be passed to a Lambda function. It's up to the Lambda function on the extreme right then to parse it and interpret it. But there's no kind of formal structure for the event. It can be anything. Hence, anything can trigger a Lambda function. But for the purpose of this diagram, anyway, all I'm saying is that all communications to your Lambda function, it all goes through this API that's provided by the Lambda service. So it's in control of it. By the way, even though it's not significant to us, your Lambdas are not running inside your VPC. They're actually running outside of VPC. You can have it such that your Lambdas are running inside a particular VPC. It's obviously more secure, but it's a little bit trickier to set that up. And I conveniently kind of avoid that in any of the stuff that I do with you. So just be aware of the fact that Lambdas by default run outside of any VPC kind of context. Now, so far our Lambda functions that we've developed in the labs, they don't really do anything other than they maybe issue a console.log to CloudWatch. But even that though, even though like by default, a Lambda function cannot communicate with any other service. This is typical AWS stuff, right? It's big on security. So you have to be explicit about what services your Lambda function can interact with. Now, even though our Lambda function did a console.log and that's all it did, we still have to give the Lambda function the permission to talk to CloudWatch logs. So a Lambda, every Lambda has what's called an execution role. So you have to actually define an IAM role and associate that IAM role with the Lambda function. And we refer to that as the execution role for your Lambda. Now, conveniently, that's done behind the scenes for us by the CDK. But if we didn't have the CDK and we had to write all of our infrastructure as code using CloudFormation templating, then we would have to create IAM roles and associate policies with those roles and then attach the role to our Lambda function so that our Lambda actually works. But CDK does that kind of behind the scenes for us. So number one, anyway, this idea of a Lambda execution role, what its purpose is, it grants the Lambda function permission to access other services. There are lots of, and we know the way IAM is kind of structured. We talk about roles and policies and permissions, and you attach a policy to a role, and the policy kind of states what what permissions are associated with that role. You're kind of familiar with all that stuff from the DevOps module. There are a number of predefined policies that the AWS people created for us just for convenience. So we call these managed policies. So there are lots of managed policies specifically related to the Lambda service. And I'm just mentioning some of them here, just kind of randomly. Although the very first one, AWS Lambda basic execution role, every Lambda function has to have this particular role associated with it. Otherwise, it wouldn't be able to talk to CloudWatch logs. Because if you looked at the detail behind this particular role, you would see that that is what it enables. It enables the possessor of the role, if you like, our Lambda function. It allows it the right to send logs to the CloudWatch service. Another example, SQS. Okay, if your Lambda wants to put messages into SQS, then there's this predefined managed policy, and so on and so forth. Right. If we just switch over to the management console for a moment, and if I go into the Lambda service, now this is the Lambda function that was created by the CDK for my little demo app with the function URLs. So if I just follow through, click on that, and here's some details on the Lambda function. And if we go down to the configuration tab, and then select permissions, you can see here I have some details on the execution role for this Lambda function. And the role itself, as I said, was auto-generated by the CDK for this Lambda, and specifically for this Lambda function. You can see from the drop-down menu here the set of services that my Lambda uses. Now, there's only one entry on it because it only uses CloudWatch logs. But if I follow through and on the role click through, then it brings me into the IAM section, or the IAM service, because that's the service that manages all of the security stuff. And if we drill down into this role and look at the permissions, so here we can see that there is one policy attached to this role, and it's one of the managed policies that I mentioned there a while ago. It's the one that it's the kind of basic policy that's associated with any Lambda function to allow it to talk to CloudWatch logs. So this is an example of a managed policy. And if I click through that to see the details of that policy, and these policies are, as you may know, are written in JSON. You can write your own custom policies, and we'll see how you do that using the CDK a little bit later on. But if we try and find the detail behind this policy, let's see, how can I do that? Yeah, if we look at the JSON here, as I said, we write these policies in raw form in JSON, but this is essentially telling me that this policy allows the entity that has this policy, our Lambda function in our case, can interact with CloudWatch. It can create CloudWatch groups, CloudWatch log streams, and it can also write to a log stream. So that's all of what's going on kind of behind the scenes. That's fine. The slight complication is there's also this thing called the resource-based policies associated with a Lambda. It's not that complicated, actually, when you think about it. The resource-based policies, they dictate who can invoke your Lambda. The execution policy dictate what your Lambda can talk to or interact with. The resource-based policy controls who can invoke your Lambda, whether the who be another service or an actual another user or another account, AWS account other than your own account. So for if you talk about another IAM principal, an IAM principal is another user. Another user can invoke a Lambda that's contained within your account if that other user has an IAM policy that grants that, or if the Lambda's resource-based policy grants it. And we're specifically interested in the resource-based policy approach. Unfortunately, again, a lot of this stuff is at the lower level anyway, is taken care of for us by the CDK based on certain instructions that we provide in the infrastructure code. So it's generating another set of policies. I was showing you a policy there a moment ago that was linked to the execution role. It also generates policies linked to the resource-based policy side of a Lambda. Right, and we will see these. It doesn't really apply to the Lambdas that we're writing so far because we're actually invoking them directly using a URL. But when we start talking about, for example, API Gateway, then API Gateway is just another service which can invoke a Lambda. And for that service to be able to invoke your Lambda, you've got to specify, or it has to be specified in that Lambda's resource-based policy that the API Gateway is allowed to do that. And we can come back to look at that maybe when it's relevant, but just for now, maybe if I just go back to the Lambda service. Here we are. Are we in the Lambda service? Are we there? No, one more tab. Okay, and if we in the configuration part, so I was talking about the execution role, but if we scroll further down, you can see there's a section here called resource-based policy as well. Okay, so I'm not going to delve into that today because we don't need to. So there's a lot of security stuff wrapped around Lambda that needs to be taken care of, all based on the IAM service, as everything related to security in AWS is centered around IAM. Now, when I started talking about Lambda last week, I said that it scales automatically based on usage, as in the more traffic that is hitting your Lambda, it scales up. And then when that traffic starts to decrease, then it scales back down again. So the little picture here is kind of illustrating that. So let's supposing I've got this Lambda function, and let's say there are two concurrent requests targeting this particular Lambda function. And because there are two concurrent requests, what the AWS Lambda service will do is it will create two instances of the Lambda, as in it will spin up two micro VM instances, load both of those instances with your Lambda code, and execute them in parallel, and send one request to one of the instances, and the other concurrent request to the other micro VM instance. on the right then. So that really just keeps on scaling. If you've got very high volume traffic, then the Lambda service just keeps on spinning up instances, micro VM instances, and loads your Lambda into them. So you could have lots and lots of instances running concurrently. Now, there is a limit though, and the limit that the AWS people arbitrarily decided was any AWS account cannot have more than 1,000 Lambda instances running concurrently, whether that be all of the same Lambda or of different Lambdas. Your total number of Lambda instances running at any particular point in time cannot exceed this upper limit of 1,000. That's just a decision that they made. You can actually request that the limit be increased. You can make a special request to the AWS, and this would be a fairly standard thing for large organizations, but certainly not in our case. Now, you can, though, I'm saying here, you can set what's called a reserved concurrency limit for any Lambda in any one of your applications. So rather than the potential of a particular Lambda within one of your applications getting up to this 1,000 figure, you can actually set an upper limit of whatever, let's say 10. And if there are 11 concurrent entries, if there are 11 concurrent requests hitting your particular Lambda, for which you have set a reserved concurrency limit of 10, then the 11th one is going to receive what's called a throttling error response. And that's a 429 status, HTTP 429 status code. That's called the throttling error code. And so if the client receives, if the client that's sending the request to your Lambda or that's trying to trigger your Lambda, and let's supposing for simplicity's sake, it's just a client that we have written rather than another AWS service. If our client receives a 429 throttling error, then the advice is that the client should delay for a period, let's say 2 seconds, and then try and make the invocation again. In the intervening time, the concurrency limit might have, the number of concurrent instances of the Lambda that you're targeting might have decreased, and so your request is processed. But let's supposing it isn't. After 2 seconds, it's not processed. You get a throttling error again. Then the advice is that you double the delay period. So we're up to 4 seconds now. Try again. If it fails again, double it again, and keep on going. Well, not keep on going, but maybe 3 or 4 iterations of that approach. So you're doubling the delay period between sequential attempts to invoke your Lambda. That's referred to as the exponential back-off algorithm approach towards dealing with throttling errors from the client's point of view. So a limit of 1,000, but you're advised maybe to set. It's a good idea to set a reservation or reserved concurrency limit on individual Lambdas, and I'll explain why in a moment in the next slide. And that's just something that you would do at the CDK level in our case. It's just another option when we're configuring our Lambdas in our CDK code. Okay, I've got that, and I've gotten that. Yeah. Now, here's an explanation as to why it's probably a good idea to set, in general, reserved concurrency limits on Lambdas. So what I'm trying to get across here, let's supposing I've got 3 different applications all running in my AWS account. The specifics aren't that important, but just to explain them. So it looks like this application up here, it has an application load balancer. It's getting very high traffic hitting it. And by the way, an application load balancer can issue requests to invoke lambdas. We're not doing it, but it can be done. So it looks like this application here is actually spinning up very high volumes of concurrent lambda instances. And let's supposing it's currently at 1,000, right? So it's reached my AWS account's upper limit for the number of concurrent lambda instances that can be that it can tolerate. But I've got another application also running in my account, and just by the way, this other application it has an API gateway, which we're not too interested in. But this other application, even though there's only one user trying to access it, this user is going to get a throttling error response back, okay, because the 1,000 limit now has been consumed by this first application. And even if I've got a third application, which can be invoked from the CLI, let's say, that's also going to get a throttling error for the same reason. So in other words, the first application on the top, it's essentially kind of hogging the concurrency limit that has been set by AWS. However, if we actually set a reserve limit for whatever this lambda is, if we set a reserve limit of, let's say, 100 on it, then these other two applications are not going to get throttling errors. And that's probably, obviously it's a balancing act, but it's probably a good idea to set some sort of reserved concurrency limit for this application because of its the nature, whatever the nature of it is. I talked about, well, I didn't talk about it that much maybe, but I did mention this notion of cold starts and warm starts for your Lambda function. So again, the way a Lambda execution works is when whatever event that triggers the Lambda, when that event occurs, the AWS service creates or it provisions a micro VM instance. It loads your code into that micro VM, and it executes the initialization code, and it then executes the handler within the Lambda. We refer to that as a cold start of our Lambda function. Cold because it had to execute the initialization code. That initialization code, you know, it can be lengthy, it can be time consuming. You know, if in the initialization code, which is typically the case, you are trying to form connections with other services, like let's say you're trying to get a connection to a DynamoDB table. So it is significant from a latency point of view, consumes a lot of time. And just to finish the story, if you remember, the warm start idea is, so let's supposing the Lambda service has spinned up a micro VM instance, loaded our Lambda code into it, executed the initialization code, and then executed the handler, and everything went fine. Let's say another request comes in, not a concurrent one now, because if it's a concurrent one, it's just going to spin up another VM and go through the same cold start process. But another request comes in after the first request has been processed, then provided the subsequent request is sometime in the immediate kind of future, and not being specific about time-wise now, but the Lambda service will reuse the micro VM that it has already spun up to handle the first request. But in this second case, it does not execute the initialization code, because any any connections that were formed are still there. In the second case, it's only going to execute the handler function itself. It's not going to run the initialization code. And so that is referred to as a warm start for the processing of that second event. But there's a significant time difference between the cold and the warm, obviously. How can you avoid these cold starts? Because they can be significant, okay? How can you avoid them? Well, there is this thing called provision concurrency, which is different now from reserved concurrency. Provision concurrency, essentially the idea is, and again, you would express the option to have provision concurrency in your infrastructure code. The idea is that the Lambda service will actually spin up a couple of micro VM instances, load your code into those instances, and run the initialization code. It will do that even though no requests have been made to your Lambda function. In other words, it's kind of provisioning some VM instances with your code ready to receive requests. So again, that's probably something that in real life production environments you would think about. Maybe should you set a provisioned concurrency value for particular lambdas within your suite of lambdas within an application, and presumably you would decide on setting a provision concurrency if the initialization code was quite lengthy in terms of the processing that it had to do. So it's just another configuration option. We won't necessarily be going into this kind of fine tuning. Just making you aware of these configuration settings.